Have you ever wondered why you can remember yesterday but not tomorrow? Why a cup of coffee goes cold but never spontaneously heats up? Why we age forward through time instead of backward? The answer lies in one of the most profound and beautiful concepts in all of science: entropy. And by the end of this video, you'll understand not just what entropy is, but why it's literally the reason time has a direction at all. Now, I know what you're thinking. Entropy sounds like one of those intimidating physics words that only people with PhDs understand. But here's the thing. Entropy is actually everywhere around you right now. It's in the way your bedroom gets messy but never cleans itself. It's in the way heat flows from your warm hands to a cold glass. It's even in the way information spreads through social media. Entropy isn't just some abstract concept locked away in textbooks. It's the invisible force that shapes literally everything about how our universe works. And here's what's really mind-blowing. Entropy might be the closest thing we have to a universal law that explains why time only moves forward. While most of physics works perfectly fine whether you're running time forward or backward, entropy gives us something called the arrow of time, a cosmic compass that points from past to future. By understanding entropy, you'll see the world in a completely different way. You'll understand why perpetual motion machines are impossible, why your phone battery always dies, and why the universe itself is slowly winding down toward what scientists call heat death. But before we dive into the deep end, let me prove to you just how universal this concept really is. I've spent months researching this topic, reading through dozens of scientific papers, and I've discovered that entropy shows up in places you'd never expect. From the way cities grow to how information is processed in computers, from the evolution of life itself to the formation of black holes, entropy is the hidden thread connecting it all. And by the time we're done, you'll have a complete understanding of one of the most important ideas in all of science. So let's start with something simple. Picture this. You walk into your room and it's perfectly clean. Everything is in its place. Your books are organized, your clothes are folded, your desk is spotless. Now, without doing any cleaning, what happens to that room over time? It gets messier, right? Clothes pile up, papers scatter, dust accumulates. Your room naturally moves from order to disorder. But here's the key question. Have you ever seen the reverse happen? Have you ever walked into a messy room and found it had spontaneously cleaned itself? Of course not. And that's entropy in action. Entropy is essentially a measure of disorder or randomness in a system. When entropy increases, things become more disordered, more random, more spread out. And here's the crucial part in any isolated system. Entropy can only increase or stay the same. It never decreases on its own. This is the second law of thermodynamics, and it's one of the most fundamental rules governing our universe. Now, let's dig deeper into what this actually means. When we say entropy is a measure of disorder, we're talking about something very specific. Imagine you have a box with a partition down the middle. On one side, you have all the air molecules. On the other side, it's empty, a perfect vacuum. This is a very ordered state because all the molecules are confined to one half of the box. But if you remove the partition, what happens? The air molecules spread out and fill the entire box. They don't stay clustered on one side, they spread out randomly, creating a more disordered state. This spreading out, this movement from order to disorder, is entropy increasing. And once those molecules have spread throughout the box, you'll never see them spontaneously return to just one side. The probability is so astronomically small that it would take longer than the age of the universe for it to happen by chance. This is why entropy is often called time's arrow. It gives us a clear direction from past to future. But here's where it gets really interesting. Entropy isn't just about air molecules in boxes. It's about energy itself. Every time energy is used to do work, some of it inevitably gets converted to heat and spreads out into the environment. This is why no machine is ever 100% efficient. Your car engine converts chemical energy from gasoline into motion, but a huge portion of that energy becomes waste heat that radiates away. Your computer converts electrical energy into computation, but it also generates heat that has to be removed by fans and cooling systems. This might seem like a limitation, like the universe is somehow flawed, but entropy isn't a bug in the cosmic code, it's a feature. It's what allows things to happen at all. Without entropy, there would be no flow of energy, no temperature differences, no driving force for any process. The universe would be a static, unchanging place where nothing could ever occur. Think about it this way. Why does water flow downhill? Because it's moving from a state of higher gravitational potential energy to lower gravitational potential energy. Why does heat flow from hot objects to cold ones? Because thermal energy is spreading out, increasing entropy. Why do batteries run down? Because the chemical energy stored in them is gradually converting to heat and spreading out into the environment. Entropy is the driving force behind every single process in the universe. And this brings us to one of the most profound implications of entropy, the concept of irreversibility. Most of the fundamental laws of physics are reversible. If you watch a video of planets orbiting the sun and play it backward, the physics still works perfectly. The equations don't care which direction time is flowing. But entropy introduces irreversibility into the world. You can watch a video of an egg falling and shattering, and you immediately know which direction is forward in time. The egg doesn't unsplatter and jump back into your hand. The entropy of the system, the disorder, has increased, and there's no going back. This irreversibility is what creates the arrow of time. Without it, the past and future would be indistinguishable. But because entropy tends to increase, we have a clear direction from lower entropy in the past to higher entropy in the future. This is why we remember the past, but not the future. Why cause comes before effect. Why we age in one direction. Now, let's explore how this plays out on different scales. At the molecular level, entropy is about the random motion of particles. In a gas, molecules are bouncing around chaotically. The temperature of the gas is actually a measure of the average kinetic energy of these molecules, how fast they're moving on average. When you heat something up, you're adding energy and making those molecules move faster and more randomly. You're increasing the entropy. But entropy isn't limited to gases. In solids, entropy shows up as vibrations in the crystal lattice. Even in the most perfect crystal, atoms are constantly jiggling around their equilibrium positions. As you heat up the solid, these vibrations increase, and eventually, the crystal structure breaks down entirely, the solid melts. This phase transition from solid to liquid is driven by entropy. The liquid state has higher entropy because the molecules have more freedom to move around. And when the liquid evaporates into a gas, that's another huge jump in entropy. Gas molecules have far more freedom than liquid molecules. They can spread out to fill any container, move in any direction, and occupy many more possible arrangements. Each phase transition represents a step up the entropy ladder. But here's something that might surprise you. Entropy can actually decrease locally. When water freezes into ice, the molecules become more ordered, arranged in a regular crystal structure. The entropy of the water decreases. So how does this fit with the second law of thermodynamics? The key is that the second law applies to isolated systems, systems that don't exchange energy or matter with their surroundings. When water freezes, it's not isolated. It's releasing heat to its surroundings, and that heat increases the entropy of the environment by more than the entropy decrease of the water itself. The total entropy of the system plus its surroundings still increases. This is how life itself is possible. Living organisms are highly ordered structures with relatively low entropy. A human body, with its intricate organs, complex biochemistry, and organized cellular structures, is far more ordered than the same mass of randomly arranged atoms. But we maintain this low entropy by constantly consuming energy from food and releasing waste heat to our environment. We're entropy decreasing machines, but we're powered by processes that increase the entropy of our surroundings by an even greater amount. This is one of the most beautiful aspects of entropy. It explains how complexity and order can emerge in a universe that's overall becoming more disordered. Stars form from collapsing gas clouds, galaxies organize themselves from primordial matter, life evolves from simple chemicals. All of these processes create local order by increasing disorder somewhere else. The universe becomes more interesting, more complex, more organized in some places, precisely because it becomes more disordered overall. And this leads us to one of the most mind-bending questions in all of science. Why was the entropy of the universe so low in the beginning? If entropy always increases, then looking backward in time, entropy must have been lower and lower. The Big Bang represents a state of incredibly low entropy, all the matter and energy in the universe compressed into an infinitesimally small point. This seems almost impossible. How could such an ordered state have existed? The answer is still one of the biggest mysteries in cosmology. Some scientists think it's related to cosmic inflation, a period of rapid expansion in the very early universe that could have smoothed out irregularities and created the low entropy initial conditions we observe. Others propose that our universe is just one of many in a multiverse, and we happen to live in one that started with low entropy because universes with high initial entropy don't evolve interesting structures like stars, planets, and life. But regardless of how it started, the consequence is clear. The universe has been on a one-way journey from order to disorder for nearly 14 billion years, and this journey is far from over. In fact, we're still in the very early stages of the universe's entropy story. Most of the stars that will ever exist haven't been born yet. The universe is still relatively young and energetic, with plenty of low-entropy energy sources like starlight and gravitational potential energy. But eventually, this will all wind down. Stars will exhaust their nuclear fuel and die. Black holes will form and slowly evaporate through Hawking radiation. The universe will expand and cool until it reaches a state of maximum entropy, a cold, dark, empty place where no more work can be done and no more interesting processes can occur. This is called heat death, and it represents the ultimate victory of entropy over order. Now, this might sound depressing, but remember we're talking about timescales that are almost incomprehensibly long. The heat death of the universe won't occur for at least 10 to the 100 years. That's a 1 followed by 100 zeros. For perspective, the universe is currently only about 10 to the 10 years old. We have plenty of time to enjoy the ride. And what a ride it is. Entropy doesn't just explain the grand fate of the universe, it explains countless phenomena in our everyday lives. It's why perfume spreads through a room, why ice cubes melt in your drink, why your smartphone gets warm when you use it intensively. It's why traffic jams form more easily than they dissolve, why rumors spread faster than corrections, why it's easier to make a mess than to clean one up. Understanding entropy also reveals why certain everyday mysteries work the way they do. Ever notice how a drop of food coloring in water spreads out until the entire glass is tinted? That's entropy driving the system toward maximum disorder. The concentrated dye represents low entropy, all those colored molecules clustered in one tiny region. But nature abhors this kind of organization. The molecules want to spread out, to explore every possible location in the glass, and entropy is the force that makes this happen. Or think about why mixing is so much easier than unmixing. You can stir cream into coffee in seconds, but try stirring it back out. You could stir for hours, days, years, it's never going to happen. The mixing process increases entropy by allowing the cream and coffee molecules to occupy far more possible arrangements. Unmixing would require all those molecules to spontaneously organize themselves back into separate regions, which violates the fundamental tendency of entropy to increase. This principle extends to information as well, which brings us to one of the most fascinating frontiers in entropy research. Information has entropy too. When you compress a file on your computer, you're essentially trying to reduce its informational entropy by finding patterns and redundancies. But there's a limit to how much you can compress any given file because truly random information has maximum entropy and can't be compressed further. Here's where it gets really wild. There's actually a deep connection between thermodynamic entropy and information entropy. When you erase information, you have to increase thermodynamic entropy somewhere else. This is called Landauer's principle, and it means that computation itself has a thermodynamic cost. Every time your computer deletes a bit of data, it has to dissipate a tiny amount of energy as heat. This is why your laptop gets warm when it's working hard. It's not just the electrical resistance in the circuits, it's the fundamental cost of processing information. This connection between information and entropy has led to some of the most profound insights in modern physics. Black holes, for instance, appear to have enormous entropy proportional to the area of their event horizon, not their volume. This suggests that all the information about the matter that fell into a black hole is somehow encoded on its surface, a concept that's revolutionizing our understanding of space, time, and reality itself. But let's bring this back to Earth for a moment. Entropy explains so many puzzles in biology and evolution. Why do species become extinct? Why do ecosystems collapse? Why do organisms age and die? In each case, entropy plays a crucial role. Species go extinct when they can no longer maintain their organized genetic information against the constant pressure of random mutations. Ecosystems collapse when the energy flows that maintain their complex structure are disrupted. And organisms age because the molecular machinery that maintains cellular organization gradually breaks down under the relentless assault of entropy. Yet paradoxically, entropy is also what makes evolution possible. Random mutations, increases in the entropy of genetic information, provide the raw material for natural selection. Without this constant injection of disorder, evolution would grind to a halt. Life harnesses entropy, using it as a source of novelty while fighting against its destructive effects through repair mechanisms and reproduction. This dance between order and disorder shows up in human society too. Cities are incredibly organized structures with roads, buildings, infrastructure, and complex social institutions. But maintaining this organization requires constant energy input, construction, maintenance, governance, economic activity. When that energy flow is disrupted, cities decay. Buildings crumble, roads crack, social structures break down. Detroit's urban decay is entropy in action on a massive scale. Even the economy follows entropy-like principles. Wealth tends to concentrate in certain areas and then disperse through trade, taxation, and spending. Market bubbles form when resources become too concentrated, creating unstable, low-entropy states that inevitably collapse as entropy reasserts itself. The 2008 financial crisis can be understood as a massive entropy increase in the financial system, all that organized. Concentrated wealth suddenly scattered across the globe through defaults, bankruptcies, and market crashes. And this brings us to one of the most important applications of entropy thinking in the modern world: sustainability. Every industrial process, every technology, every human activity involves entropy production. We take organized resources like fossil fuels or minerals and convert them into products, but we always produce waste heat and disorder in the process. The challenge of sustainable development is essentially an entropy management problem. How do we maintain the organized structures of human civilization while minimizing the entropy we dump into our environment? Renewable energy sources like solar and wind are appealing partly because they tap into entropy flows that are already happening. The sun is constantly converting organized nuclear energy into dispersed heat and light. Wind is driven by temperature differences that represent entropy gradients in the atmosphere. By capturing some of this energy before it fully dissipates, we can power our civilization while working with the universe's natural entropy flows rather than against them. This perspective also explains why recycling is thermodynamically challenging. When we use materials, we typically disperse them, mix different metals together in complex alloys, combine plastics with additives, spread chemicals throughout products. Recycling requires us to reverse this process, to decrease entropy by separating and purifying materials. This takes energy, often more energy than making new materials from raw resources. Perfect recycling is thermodynamically impossible. There's always some entropy increase, some loss of organization, some degradation in quality. But here's the remarkable thing about entropy: despite being fundamentally about disorder and decay, it's also the engine of all change, all progress, all interesting phenomena in the universe. Without entropy, nothing would ever happen. Energy would remain forever locked in place, unable to flow from one form to another. There would be no temperature differences to drive weather, no chemical gradients to power life, no information processing to enable consciousness. Entropy is what makes time flow forward, but it's also what makes time meaningful. In a universe without entropy, where all processes were perfectly reversible, there would be no distinction between past and future, no history, no memory, no growth, no learning. The arrow of time that entropy creates isn't just a mathematical curiosity, it's what allows stories to unfold, civilizations to rise, consciousness to emerge. Think about your own life story. It's fundamentally an entropy story. You started as a highly organized, fertilized cell and grew into an even more organized adult human. But this organization came at the cost of increasing entropy elsewhere. All the food you've eaten, the energy you've consumed, the waste you've produced. Your life is a temporary victory of organization over disorder, powered by the constant flow of entropy through your body. And your memories, your experiences, your knowledge, these are all forms of information that you've organized and stored. Your brain is constantly fighting against informational entropy, maintaining the neural patterns that encode your thoughts, skills, and memories. When you learn something new, you're creating order in your neural networks. When you forget, entropy wins a small victory. This is why entropy isn't just a physics concept. It's a lens for understanding everything from personal growth to social change to cosmic evolution. It explains why maintaining relationships requires effort, why skills deteriorate without practice, why organizations need constant management to avoid chaos. Entropy is always there in the background, the universal force that ensures nothing stays the same forever. But perhaps most importantly, understanding entropy gives us a deeper appreciation for the extraordinary nature of our existence. In a universe trending toward maximum disorder, we are islands of incredible organization. The atoms in your body were forged in the cores of dying stars, scattered through space, and somehow came together to form the complex, thinking, feeling being that is you. Against all odds, against the fundamental tendency of the universe, you exist as a temporary but magnificent victory of order over chaos. And that victory isn't just personal, it's shared by every living thing, every planet, every star, every galaxy. The entire cosmic story is one of entropy creating the conditions for organization to emerge, flourish, and eventually give way to new forms of order. We're all participants in this grand entropy dance, this cosmic ballet between order and disorder that has been playing out for nearly 14 billion years. As we continue this journey through entropy, let's pause for a moment and consider something that might blow your mind. You've probably heard that the universe is expanding, that galaxies are racing away from each other at incredible speeds. But here's what's really fascinating. This expansion isn't just about space getting bigger, it's about entropy winning on the largest possible scale. When the universe expands, it's not just stretching space, it's diluting energy. Think of it like this. Imagine you have a concentrated drop of dye in a small glass of water. The dye is intense, vibrant, highly concentrated. But if you keep adding water to the glass, that same amount of dye becomes more and more diluted until eventually you can barely see it. The expansion of the universe is doing the same thing to energy itself. All the energy that was packed into the incredibly dense, hot state of the Big Bang, is being spread thinner and thinner across an ever-growing volume of space. This is entropy increase on a cosmic scale. The universe isn't just getting bigger, it's getting colder, more dilute, more spread out. And this process is accelerating. Dark energy, that mysterious force that's driving the expansion faster and faster, is essentially entropy's cosmic accomplice, ensuring that the universe becomes increasingly disordered at the grandest possible scale. But here's where the story gets truly mind-bending. While the universe is expanding and cooling, entropy is simultaneously creating the conditions for the most complex structures we know to emerge. This seems like a contradiction at first. How can increasing disorder lead to increasing complexity? The answer lies in understanding that entropy doesn't just destroy it, also creates gradients. And gradients are what make interesting things happen. Think about a mountain range. Mountains form because of energy gradients in the Earth's crust, differences in temperature, pressure, and composition that drive tectonic activity. As these gradients try to equalize, as entropy increases, they create the spectacular geological features we see around us. The same principle applies throughout the universe. Stars form because gravity creates density gradients in gas clouds. When these gradients collapse under their own weight, they create the nuclear furnaces that light up the cosmos. Even more remarkably, these stellar furnaces are entropy engines of incredible sophistication. Inside a star's core, hydrogen nuclei are being fused into helium, converting mass directly into energy, according to Einstein's famous equation E mach squared. This process releases enormous amounts of energy, but it also increases entropy by creating heat and light that radiate away into space. The star is essentially burning through its nuclear fuel, converting organized matter into disorganized energy. And when that fuel runs out, the star dies, often in a spectacular supernova explosion that scatters heavy elements throughout space. These elements, carbon, oxygen, nitrogen, iron, and dozens of others, are the building blocks of planets, life, and everything we see around us. Your body contains atoms that were forged in the nuclear fires of stars that died billions of years ago. You are literally made of stardust, and that stardust exists because of entropy-driven processes in stellar cores. This brings us to one of the most profound questions in all of science. How did life emerge in a universe governed by entropy? At first glance, it seems impossible. Life represents an incredible level of organization, complex molecules, arranged in precise patterns, information encoded in DNA, cellular structures that maintain themselves with remarkable precision. How can such order arise in a universe that's fundamentally trending toward disorder? The answer is that life doesn't violate the second law of thermodynamics, it exploits it. Living organisms are what scientists call dissipative structures. They maintain their organization by constantly consuming energy and producing entropy. A tree, for example, captures sunlight and uses it to build complex organic molecules from simple carbon dioxide and water. But in the process, it generates waste heat that increases the entropy of its environment by more than the entropy decrease represented by its growth. This is true for every living thing, including you. Right now, as you're watching this video, your body is running thousands of chemical reactions that maintain your cellular organization. Your heart is pumping blood, your brain is processing information, your digestive system is breaking down food. All of these processes require energy, and all of them produce waste heat that gets dissipated into your environment. But here's what's truly remarkable about life. It doesn't just maintain organization, it creates new forms of organization. Evolution is essentially an entropy-driven process that generates increasingly complex and sophisticated forms of order. Random mutations introduce entropy into genetic information, but natural selection filters this randomness, preserving changes that improve survival and reproduction while discarding harmful ones. Over billions of years, This process has produced the incredible diversity of life we see today. From simple bacteria to complex ecosystems, from individual organisms to collective behaviors like flocking and swarming, evolution has created layer upon layer of organization. And all of it is powered by entropy, the same force that makes your coffee cool down and your room get messy. This evolutionary process continues today, not just in biological systems, but in human culture and technology. Languages evolve through random changes and selective pressures. Technologies improve through trial and error, with successful innovations spreading while failures are forgotten. Even ideas themselves undergo a kind of natural selection, with useful concepts surviving and spreading, while impractical ones fade away. And now we're witnessing something unprecedented in the history of the universe, the emergence of artificial intelligence. AI systems are essentially entropy processing machines, taking in vast amounts of disorganized data and finding patterns, creating models, generating new information. They're doing what life has always done, creating local order by processing entropy, but at speeds and scales that were impossible just a few decades ago. This raises fascinating questions about the future of entropy and organization in the universe. Could artificial intelligence represent the next major step in the cosmos's ability to create complex, organized structures? Could we eventually develop technologies that are so efficient at harvesting and organizing energy that they could significantly slow down the universe's march toward heat death? These aren't just science fiction fantasies, they're serious questions being explored by physicists and cosmologists today. Some researchers have proposed that sufficiently advanced civilizations could potentially reverse entropy on local scales, creating islands of decreasing entropy in an otherwise increasingly disordered universe. Others suggest that the ultimate fate of intelligence in the universe might be to spread throughout the cosmos, harvesting energy from stars, black holes, and even the expansion of space itself. But let's zoom back down to Earth for a moment, because entropy has profound implications for how we think about human society and our future as a species. Every civilization that has ever existed has faced the fundamental challenge of entropy, how to maintain organized structures in the face of constant decay and disorder. Empires rise and fall. Cities are built and crumble. Knowledge is created and lost. History is full of examples of societies that failed to manage their entropy flows and collapsed as a result. The Roman Empire, for instance, became increasingly complex over time, developing elaborate bureaucracies, extensive trade networks, and sophisticated military organizations. But maintaining this complexity required enormous amounts of energy, resources, manpower, communication systems. When the empire could no longer sustain these energy flows, entropy took over. Roads fell into disrepair, trade networks broke down, knowledge was lost, and the complex Roman system fragmented into simpler, more disordered pieces. This pattern repeats throughout history. The Maya civilization developed incredibly sophisticated astronomical knowledge, complex writing systems, and elaborate urban centers. But when climate change disrupted their agricultural systems, they could no longer maintain the energy flows needed to support their complex society. Entropy won, and their cities were abandoned to the jungle. Today, we face similar challenges on a global scale. Our modern technological civilization is incredibly complex, dependent on intricate supply chains, sophisticated infrastructure, and vast energy flows. We've created a global system that processes enormous amounts of matter and energy, converting raw materials into products, information, and waste. But this system is also incredibly fragile, vulnerable to disruptions that could trigger cascading entropy increases. Climate change, for example, isn't just about rising temperatures, it's about increasing entropy in the Earth's climate system. As we pump greenhouse gases into the atmosphere, we're adding energy to the system, making weather patterns more chaotic, more extreme, more unpredictable. This increased climatic entropy threatens the organized systems we depend on: agriculture, water supplies, coastal cities, transportation networks. The challenge of sustainability is fundamentally an entropy management problem. How do we maintain the organized structures of modern civilization while minimizing the entropy we produce? How do we design economic systems that work with natural entropy flows rather than against them? How do we create technologies that are more efficient at converting energy into useful work and less wasteful in their entropy production? These questions are driving some of the most important research and development efforts of our time. Renewable energy technologies aim to capture entropy flows that are already happening: sunlight, wind, flowing water, rather than creating new entropy through fossil fuel combustion. Circular economy concepts try to minimize waste by designing systems where the outputs of one process become inputs for another, reducing the overall entropy production. Advanced materials research is focused on creating substances that can maintain their organization under extreme conditions, resisting the natural tendency toward disorder. Nanotechnology promises to give us unprecedented control over matter at the atomic scale, potentially allowing us to build structures with incredibly low entropy and high efficiency. But perhaps the most exciting frontier is in information technology and artificial intelligence. As we mentioned earlier, there's a deep connection between information and entropy. Every computation involves converting one form of information into another, and this process has thermodynamic consequences, but it also offers incredible opportunities. Consider what happens when you use a GPS navigation system. The system takes in vast amounts of entropy radio signals from satellites, data about traffic patterns, information about road conditions and processes, all of this chaotic input to produce something incredibly organized, turn-by-turn directions that get you efficiently from point A to point B. The system is essentially creating order from disorder, using computational power to fight against entropy. Now imagine scaling this up. What if we could develop AI systems sophisticated enough to optimize entropy flows on a global scale? Systems that could coordinate energy distribution, optimize supply chains, predict and prevent system failures before they cascade into larger disruptions? We might be able to create a kind of global nervous system that helps humanity manage entropy more efficiently than ever before. But there's also a darker side to consider. Information technology itself consumes enormous amounts of energy. Data centers that power the internet use as much electricity as entire countries. Every Google search, every Netflix stream, every TikTok video represents energy consumption and entropy production. As our digital lives become more complex, the thermodynamic cost of maintaining our information systems grows exponentially. This creates a kind of entropy paradox. The more sophisticated our information processing becomes, the more energy it requires, and the more entropy it produces. We're using increasingly complex systems to fight entropy, but those systems themselves are major entropy producers. It's like trying to bail out a sinking boat with a pump that's powered by drilling holes in the hull. Understanding this paradox is crucial for our future. We need to develop information technologies that are not just more powerful, but more thermodynamically efficient. We need quantum computers that can process information with minimal energy consumption. We need biological computing systems that harness the incredible efficiency of cellular processes. We need to learn from nature's 4 billion years of experience in managing entropy flows. Because here's the thing, life on Earth has already solved many of the entropy management problems we're struggling with. Photosynthesis converts sunlight into chemical energy with remarkable efficiency. Cellular repair mechanisms maintain molecular organization against constant entropy assault. Ecosystems process nutrients and energy in complex cycles that minimize waste and maximize sustainability. By studying these biological systems, we're learning to design human technologies that work more like life itself, systems that can maintain organization while producing minimal entropy, that can repair themselves when damaged, that can adapt and evolve in response to changing conditions. This biomimetic approach to technology could be the key to creating a truly sustainable civilization. But even if we solve all these technical challenges, Even if we develop technologies that can efficiently manage entropy on any scale we choose, we still face the ultimate entropy challenge, the heat death of the universe itself. No matter how clever we become, no matter how advanced our technologies, we can't escape the fundamental fact that the universe is running down. Or can we? This is where science begins to sound like science fiction, but it's worth considering. Some physicists have proposed that sufficiently advanced civilizations might be able to influence the large-scale structure of the universe itself. They might harness the energy released by black hole evaporation, or tap into the expansion of space itself as an energy source. They might even be able to create new universes with more favorable entropy conditions. These ideas push the boundaries of what we consider possible, but they highlight something important about entropy and the arrow of time. While entropy gives time its direction, it doesn't necessarily dictate the ultimate fate of intelligence and organization in the universe. Life and intelligence represent something truly remarkable: patterns of matter and energy that can understand entropy, work with it, and potentially transcend its limitations. You are part of this cosmic story. Every thought you think, every decision you make, every action you take is part of the universe's ongoing experiment with organization and complexity. You're a temporary but magnificent arrangement of atoms that can contemplate its own existence, understand the forces that shaped it, and potentially influence the future direction of entropy in the cosmos. This perspective can be both humbling and empowering. Humbling because it reminds us that we're all part of something much larger than ourselves, subject to forces and processes that operate on scales we can barely comprehend. But empowering because it shows us that consciousness, intelligence, and creativity represent genuine victories over entropy, rare and precious phenomena in a universe that tends toward disorder. And this brings us to one of the most mind-bending realizations in all of science. Entropy isn't just something that happens to matter and energy. It happens to space and time themselves. When Einstein showed us that space and time are woven together into a single fabric called space-time, he also revealed that this fabric can be stretched, warped, and twisted. And guess what governs these changes? That's right, entropy. Black holes represent entropy taken to its absolute extreme. These cosmic monsters are regions where matter has collapsed so completely that space and time themselves break down at the center. But here's the really wild part. Black holes have temperature and entropy just like any other thermodynamic system. In fact, they have more entropy than anything else we know of in the universe. A black hole with the mass of our Sun has an entropy that's larger than the entropy of every atom, every molecule, every star in our entire galaxy combined. This discovery, made by physicist Jacob Bekenstein and later refined by Stephen Hawking, completely revolutionized our understanding of entropy. It showed us that entropy isn't just about the arrangement of particles, it's about the fundamental structure of reality itself. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This means that all the information about everything that ever fell into the black hole is somehow encoded on its surface, like a cosmic hologram. Think about what this implies. If you fell into a black hole, from your perspective, you'd cross the event horizon and eventually reach the singularity at the center. But from the outside observer's perspective, all the information about you, every detail of your physical structure, every memory, every thought would be smeared across the black hole's surface as a two-dimensional pattern. You'd become part of the black hole's entropy, encoded in the quantum fluctuations of its event horizon. This isn't just theoretical speculation. Recent advances in quantum information theory suggest that this holographic principle might apply to the entire universe. Some physicists now believe that all of three-dimensional reality might be encoded on a two-dimensional surface at the edge of the observable universe. If they're right, then everything you see around you, this room, this planet, your own body, might be a kind of holographic projection from information stored on a distant cosmic boundary. But let's bring this back to something more concrete. You know how we said entropy always increases in isolated systems? Well, black holes seem to violate this rule. When Stephen Hawking calculated the quantum effects near a black hole's event horizon, he discovered something shocking: black holes actually evaporate. They emit radiation, now called Hawking radiation, that slowly carries away their mass and energy. Here's where it gets really weird. As a black hole evaporates, its entropy decreases. The information that was encoded on its event horizon gets released back into the universe as thermal radiation. But there's a problem. Thermal radiation is essentially random. It doesn't carry specific information about the things that fell into the black hole. So where does all that information go? Does it just disappear, violating one of the most fundamental principles of quantum mechanics? This is called the black hole information paradox, and it's been driving physicists crazy for decades. Some think the information is destroyed, which would mean the universe isn't fundamentally reversible. Others believe the information is preserved in subtle correlations in the Hawking radiation that we just don't know how to detect yet. Still, others propose that the information gets transferred to parallel universes through quantum entanglement. The resolution of this paradox will likely require a complete theory of quantum gravity, a framework that can describe how space-time itself behaves at the quantum level, and entropy is at the heart of this quest. Understanding how information and entropy behave in extreme gravitational environments might be the key to unlocking the deepest secrets of the universe. But even without solving these cosmic puzzles, we can see entropy's fingerprints everywhere in our daily lives. Take your smartphone, for example. Every time you take a photo, send a text, or stream a video, you're manipulating entropy in incredibly sophisticated ways. The camera sensor converts photons into electrical signals, creating organized digital information from chaotic light patterns. The processor performs millions of calculations, transforming that information into recognizable images and sounds. The screen emits precisely controlled light patterns that your brain interprets as pictures and text. All of this happens because engineers have learned to harness entropy flows with incredible precision. The battery in your phone stores chemical energy in an organized state: electrons confined to specific molecules, ready to flow through circuits when needed. As you use the phone, this organized energy gets converted into computation, light, sound, and ultimately waste heat that makes the device warm to the touch. But here's something most people don't realize. Every bit of information stored on your phone has a thermodynamic cost. When you delete a photo, your phone doesn't just remove it from memory, it has to physically reset the transistors that were storing that data. And according to Landauer's principle, every bit of information that gets erased requires a minimum amount of energy to be dissipated as heat. It's an incredibly tiny amount, about 10 circumflex negative 21 joules per bit at room temperature, but it's a fundamental limit imposed by the laws of thermodynamics. This means that computation itself is an entropy-producing process. Every calculation, every data transfer, every logical operation increases the entropy of the universe by a tiny amount. As our digital civilization becomes more complex, as we store more data and run more calculations, we're contributing to the universe's overall entropy in ways our ancestors never could have imagined. And this brings us to one of the most fascinating frontiers in modern physics: the relationship between consciousness and entropy. Your brain, right now, is performing computations that make your smartphone look like a pocket calculator. It's processing sensory information, storing and retrieving memories, generating thoughts and emotions, and somehow creating the subjective experience of being you. All of this mental activity has a thermodynamic cost. Your brain uses about 20% of your body's total energy consumption, despite being only 2% of your body weight. That energy goes into maintaining the electrical gradients across neural membranes, synthesizing neurotransmitters, and performing the countless chemical reactions that keep your neurons functioning. And like every other energy-consuming process, it produces entropy in the form of waste heat. But here's where things get really interesting. Consciousness seems to involve something that looks very much like entropy reduction. When you perceive something, you're taking chaotic sensory input, millions of photons hitting your retina, sound waves vibrating your eardrums, molecules triggering your taste and smell receptors and organizing it into coherent perceptions. You're creating order from disorder, at least locally in your brain. When you form a memory, you're encoding information in the synaptic connections between neurons, creating organized patterns that can persist for years or even decades. When you solve a problem, you're taking disorganized thoughts and organizing them into logical sequences. In a very real sense, consciousness is an entropy processing machine, constantly working to create local order while contributing to global disorder. This has led some scientists to propose that consciousness might be fundamentally connected to entropy and information processing. The integrated information theory, developed by neuroscientist Giulio Tononi, suggests that consciousness corresponds to the amount of integrated information in a system, essentially, how much the system reduces uncertainty about its own states. If this theory is correct, then consciousness isn't just something that happens to produce entropy, it's something that emerges from entropy processing itself. The more complex and integrated a system's information processing becomes, the more conscious it becomes. This could explain why humans seem more conscious than other animals, why some brain injuries affect consciousness more than others, and why anesthetics work by disrupting information integration in the brain. And it raises profound questions about the future of consciousness in the universe. As we develop more sophisticated artificial intelligence systems, as we create computers that can process information in increasingly complex and integrated ways, are we potentially creating new forms of consciousness? Could artificial minds eventually become conscious in the same way human minds are, through the same entropy processing mechanisms? These questions become even more intriguing when we consider the possibility of uploading human consciousness to computers. If consciousness really is just a pattern of information processing, then theoretically it should be possible to replicate that pattern in a different substrate. You could potentially achieve a kind of immortality by transferring your mind to a computer system that's more resistant to entropy than your biological brain. But this raises deep questions about identity and continuity. If your consciousness is uploaded to a computer, is the digital version really you, or is it just a copy? And if your original brain continues to exist alongside the digital copy, which one has the stronger claim to being the real you? These aren't just philosophical puzzles, they're practical questions about the nature of consciousness and identity that we might need to answer within the next few decades. Meanwhile, back in the biological world, entropy continues to shape the evolution of life in ways we're only beginning to understand. Consider the incredible diversity of life on Earth, millions of species, each with their own unique adaptations, behaviors, and ecological roles. This diversity isn't random, it's the product of entropy-driven processes operating over billions of years. Random mutations introduce entropy into genetic information, creating variations in traits. Environmental pressures then select for some variations while eliminating others, effectively filtering the entropy and preserving organized patterns that enhance survival and reproduction. Over time, this process generates increasingly complex and sophisticated forms of organization. But evolution isn't just about individual organisms, it's also about the emergence of collective behaviors and social structures. Ant colonies, beehives, flocks of birds, schools of fish. These are all examples of organized systems that emerge from the interactions of simpler components. No individual ant has a blueprint for the entire colony. No single bee plans the hive's architecture. Instead, complex organization emerges from simple rules and local interactions, creating order from apparent chaos. Humans have taken this process to unprecedented levels. We've created languages that allow us to share information across generations, preserving knowledge and reducing cultural entropy. We've developed technologies that extend our capabilities far beyond what any individual could achieve alone. We've built institutions, governments, universities, corporations that can maintain their organization across decades or centuries, passing information and purpose from one generation to the next. And now we're on the verge of creating artificial systems that might be able to participate in this evolutionary process alongside us. Machine learning algorithms already exhibit something that looks like evolution. They generate random variations in their parameters, test these variations against data, and keep the changes that improve performance while discarding those that don't. As these systems become more sophisticated, they might begin to evolve in ways that are genuinely creative and unpredictable. This could lead to a kind of hybrid evolution, where biological and artificial intelligence co-evolve together, each driving the development of the other. Humans might enhance themselves with artificial components, while AI systems might incorporate biological elements. The boundary between natural and artificial, between organic and digital, might become increasingly blurred. But regardless of what forms intelligence takes in the future, it will always be subject to the fundamental constraints imposed by entropy. Every thought, every calculation, every act of creation or preservation requires energy and produces waste heat. The more complex our minds become, the more entropy they generate. This isn't a limitation to be overcome, it's a fundamental feature of how information processing works in our universe. And this brings us back to the arrow of time. Consciousness, memory, and identity are all intimately connected to time's direction. You remember the past because your brain has recorded information about previous states, creating organized patterns that resist entropy. You anticipate the future by using that stored information to make predictions about what might happen next. Your sense of self is fundamentally tied to the continuity of your memories over time. Without entropy, without the arrow of time, consciousness as we know it couldn't exist. There would be no distinction between past and future, no accumulation of memories, no learning or growth. The universe would be a static, timeless place where nothing could ever change or develop. So when you think about entropy, don't just think about decay and disorder. Think about the incredible creativity and complexity that emerges from entropy's relentless drive toward equilibrium. Every star that shines, every life that grows, every thought that forms is a temporary victory of organization over chaos, powered by the same fundamental force that makes your coffee grow cold and your room grow messy. You are part of this cosmic story, a pattern of matter and energy that can understand its own existence, contemplate the forces that shaped it, and potentially influence the future direction of complexity in the universe. In a cosmos trending toward maximum entropy, you represent something truly extraordinary, organized matter that has become aware of itself, capable of creating meaning, beauty, and purpose in the face of inevitable decay. And perhaps that's the most profound lesson entropy has to teach us. Not that everything is doomed to decay, but that the temporary patterns of organization we call stars, planets, life, and consciousness are precious precisely because they're temporary. They're islands of order in an ocean of chaos, brief candles burning against the darkness of universal entropy. The arrow of time points forward, toward a future of increasing entropy and decreasing order. But along the way, in the space between the organized past and the chaotic future, there's room for wonder, for discovery, for love, for all the things that make existence meaningful. Entropy doesn't just drive the universe toward heat death, it creates the conditions where life, consciousness, and beauty can emerge and flourish, however briefly, in the cosmic dance of order and disorder. And that brings us to one of the most mind-bending implications of entropy that most people never consider. It's not just shaping our universe, it's creating multiple universes. Stay with me here, because this is where entropy theory gets truly wild. You see, every time a quantum event occurs, every time an electron decides which path to take, every time a particle decays, every time any quantum measurement happens, entropy is making a choice. And according to some interpretations of quantum mechanics, it's not just making one choice, it's making all possible choices simultaneously, branching the universe into countless parallel realities. Think about it this way. Right now, as you're watching this video, Quantum events are happening in your brain, electrons jumping between energy states in your neurons, quantum tunneling events in your synapses. Each of these events could go multiple ways, and if the many worlds interpretation is correct, they do go every way. There's a version of you in a parallel universe who just decided to skip ahead in this video, another who paused to grab a snack, and countless others experiencing slightly different versions of this exact moment. From Entropy's perspective, this multiplication of realities is the ultimate expression of increasing disorder. Instead of one organized timeline, we get an exponentially growing tree of possibilities, each branch representing a different way events could unfold. The total entropy across all these parallel universes is vastly larger than the entropy of any single universe could ever be. But here's what's really fascinating. If this interpretation is correct, then consciousness itself might be an entropy navigation system. Your awareness, your sense of experiencing one particular sequence of events, rather than all possible sequences simultaneously, could be the universe's way of exploring the space of possibilities. Every conscious being becomes a kind of entropy probe, sampling one particular path through the infinite maze of quantum possibilities. This has profound implications for free will and decision-making. When you choose between options, say, whether to continue watching this video or switch to something else, you might not be creating your choice so much as selecting which branch of reality to experience. The entropy of your brain state, the random quantum fluctuations in your neural networks, could be the mechanism that determines which version of yourself you become from moment to moment. Now, let's zoom out even further and consider entropy on the largest possible scales. We've talked about the heat death of the universe, that distant future when all the stars have burned out and all the black holes have evaporated. But recent discoveries in cosmology suggest that even this isn't the end of entropy's story. Dark energy, the mysterious force that's accelerating the expansion of our universe, appears to be a property of empty space itself. As the universe expands, more empty space gets created, and with it, more dark energy. This creates a runaway process. The more the universe expands, the more dark energy there is to drive even faster expansion. Some cosmologists predict that this could lead to a scenario called the Big Rip, where the expansion becomes so rapid that it literally tears apart the fabric of space-time itself. First, galaxies would be pulled apart from each other. Then solar systems would separate. Eventually, even atoms would be ripped apart as space expands faster than the forces holding matter together can compensate. From an entropy perspective, the Big Rip would represent the ultimate victory of disorder over organization. Not just the heat death of matter and energy, but the complete dissolution of space-time itself into quantum chaos. Its entropy taken to its absolute logical extreme, the universe literally coming apart at the seams. But even this apocalyptic scenario might not be the final word. Some theories suggest that the destruction of space-time could trigger the birth of new universes, new Big Bangs, emerging from the quantum foam of collapsed reality. If true, this would make entropy not just the force that drives our universe toward its end, but the creative force that gives birth to infinite new universes in an eternal cycle of destruction and rebirth. This brings us back to a question we touched on earlier, the mystery of why our universe started with such low entropy in the first place. If the Big Bang represented a state of incredibly low entropy, incredibly high organization, how did it get that way? One possibility is cosmic inflation, that period of rapid expansion in the universe's first fraction of a second. But inflation itself requires very specific initial conditions to work properly. Another possibility is that our universe isn't unique. Maybe there's a vast multiverse containing countless universes, each with different initial conditions, different physical laws, different entropy states. We happen to live in one of the rare universes that started with low entropy, because those are the only universes where complex structures like stars, planets, and life can form. It's a kind of cosmic selection effect. We observe a low entropy universe because we couldn't exist in a high entropy one. But here's where things get really speculative. Some physicists have proposed that intelligent civilizations might eventually become powerful enough to influence the large-scale structure of space-time itself. If consciousness really is the universe's way of fighting entropy, then perhaps sufficiently advanced consciousness could actually reverse entropy on cosmic scales. Imagine a civilization that has spread throughout its galaxy, harvesting energy from every star, every black hole, every quantum fluctuation in empty space. Such a civilization might be able to manipulate matter and energy on scales we can barely imagine. They might be able to create new stars, prevent the heat death of their local region, or even engineer new universes with more favorable entropy conditions. This isn't just science fiction speculation, it's a serious area of research called cosmological engineering. Physicists have calculated that it might be theoretically possible for advanced civilizations to create false vacuum bubbles that expand into new universes, or to manipulate the expansion rate of space-time itself. If intelligence can spread throughout the cosmos and develop these capabilities, then the ultimate fate of entropy in our universe might not be predetermined after all. But let's bring this back to Earth and talk about something more immediate, how understanding entropy can actually change the way you live your life. Because once you really grasp what entropy means, once you understand that you're a temporary pattern of organization in a universe trending toward disorder, it puts everything in perspective. Your relationships, for example, require constant energy input to maintain their organization. Just like a biological cell needs to constantly repair molecular damage to stay alive, a friendship or romance needs ongoing effort, communication, and care to prevent the entropy of misunderstanding and drift from taking over. The couples who stay together aren't the ones who never have problems, they're the ones who consistently invest energy in maintaining and rebuilding their connection. Your skills and knowledge are the same way. Everything you've learned, every ability you've developed, is a form of organization in your neural networks. But neural entropy is always at work. Connections weaken, memories fade, skills atrophy without practice. The phrase "use it or lose it" is literally describing entropy in action. Maintaining expertise requires constant energy input, constant practice, constant learning. Even your physical health is fundamentally an entropy management problem. Your body is continuously fighting against molecular damage, cellular degradation, and systemic breakdown. Exercise doesn't just build muscle, it's an anti-entropy activity that maintains the organization of your cardiovascular system, your bones, your neural networks. The reason sedentary lifestyles are so unhealthy isn't just that you're not building fitness, it's that you're allowing entropy to win by default. This perspective can be liberating because it removes the illusion that maintaining organization should be effortless. Your room gets messy not because you're lazy, but because entropy is one of the most fundamental forces in the universe. Your skills need practice not because you're inadequate, but because entropy affects everything, including neural connections. Understanding this can help you be more compassionate with yourself, while also being more strategic about where you invest your anti-entropy efforts. And this brings us to one of the most practical applications of entropy thinking decision-making under uncertainty. Every choice you make is essentially a bet about how different paths will affect the entropy of your future. Should you take that job offer? Go back to school? Move to a different city? End a relationship? Start a new project? From an entropy perspective, these decisions involve weighing different types of order and disorder. Taking a new job might decrease the entropy of your financial situation, while potentially increasing the entropy of your work-life balance. Going back to school might create more organization in your knowledge and skills while introducing chaos into your schedule and budget. Every major life decision involves entropy trade-offs. But here's something most people don't realize. Uncertainty itself is a form of entropy. When you're facing a difficult decision, part of what makes it stressful is the high entropy of your information state. You have multiple possible futures swirling around in your mind, and you can't predict which outcomes will actually occur. Making a decision doesn't eliminate all uncertainty, but it does reduce the entropy of your mental state by committing to one path forward. This is why indecision can be so exhausting. When you're stuck between options, your brain is constantly running simulations of different possibilities, trying to predict outcomes, weighing pros and cons. This mental activity consumes glucose, generates heat, and quite literally increases entropy in your neural networks. Sometimes the best choice isn't the objectively optimal choice. It's any choice that reduces the entropy of prolonged uncertainty. Speaking of mental entropy, let's talk about information overload in the modern world. Every day, you're bombarded with vastly more information than any human in history. News feeds, social media, emails, messages, notifications, advertisements. It's a constant stream of data competing for your attention. From an entropy perspective, this represents a massive increase in the disorder of your information environment. Your brain has limited capacity for processing and organizing information. When the input rate exceeds your processing capacity, entropy increases. You feel overwhelmed, scattered, unable to focus. This isn't a personal failing, it's a thermodynamic constraint. Just like a computer can be overwhelmed by too much data, your neural networks can be overwhelmed by too much information entropy. This is why information diets and digital minimalism have become so important. By consciously reducing the entropy of your information inputs, unsubscribing from unnecessary feeds, setting boundaries on social media, creating quiet spaces for deep thinking, you give your brain the resources it needs to maintain its own internal organization. You're essentially managing your personal information entropy to optimize for clarity and focus. The same principle applies to physical environments. Cluttered spaces aren't just aesthetically unpleasant, they increase the entropy of your sensory environment, making it harder for your brain to process information efficiently. This is why many people find that cleaning and organizing their space helps them think more clearly. You're literally reducing environmental entropy to support mental organization. And this connects to something fascinating about human creativity. Some of the most creative insights emerge not from highly organized thinking, but from allowing controlled amounts of entropy into your mental processes. When you let your mind wander, when you expose yourself to random inputs, when you make unexpected connections between disparate ideas, you're introducing entropy into your thinking in a way that can lead to novel organizations of knowledge. This is why activities like walking, showering, or doing simple tasks often trigger creative breakthroughs. These activities occupy the organized, analytical parts of your brain, just enough to allow more chaotic, associative processes to take over. You're temporarily increasing the entropy of your thought patterns, which creates space for new connections to form. The history of scientific discovery is full of examples of entropy-driven insights. Darwin's theory of evolution emerged from his observation of random variations in species entropy at the biological level, combined with selective pressures that create order from chaos. Einstein's relativity theories came from imagining what would happen if you could ride alongside a beam of light, a thought experiment that introduced entropy into his assumptions about absolute space and time. Even this video you're watching represents a kind of entropy management. I've taken the chaotic complexity of entropy theory, thousands of research papers, competing interpretations, mathematical formulations, and organized it into a linear narrative that your brain can process sequentially. I'm reducing the entropy of the information to make it more accessible, while hopefully preserving the essential insights that make entropy so fascinating. But here's something that might surprise you. The act of learning itself is an entropy process. When you encounter new information, it initially increases the entropy of your knowledge state. New facts don't automatically fit into your existing mental models. They create cognitive dissonance, confusion, uncertainty. Your brain has to work to integrate this new information, to reorganize your existing knowledge structures to accommodate it. This is why learning can be uncomfortable. especially when you encounter ideas that challenge your existing beliefs. Your brain is literally fighting entropy, working to maintain coherent mental models in the face of disruptive new information. The students who succeed aren't necessarily the ones who find learning easy. They're the ones who develop tolerance for the temporary entropy increase that comes with intellectual growth. And this brings us to one of the most profound implications of entropy for human society: the importance of education and knowledge preservation. Every generation of humans represents a temporary victory over entropy, a brief flowering of organized intelligence in an otherwise chaotic universe. But knowledge and culture are fragile. They require constant energy input to maintain across generations. Languages disappear when communities stop speaking them. Skills are lost when practitioners don't pass them on to apprentices. Scientific knowledge can be forgotten if it's not continuously taught and applied. The burning of the Library of Alexandria wasn't just a tragedy because of the specific books that were lost. It was a massive entropy increase, a sudden disorder imposed on one of humanity's greatest attempts at organizing knowledge. This is why libraries, schools, and universities are so important from an entropy perspective. They're not just repositories of information, they're active systems for fighting entropy, for maintaining and transmitting organized knowledge across time. Every teacher, every textbook, every educational video is part of humanity's ongoing battle against intellectual entropy. And in our digital age, this battle has taken on new dimensions. We can now store vastly more information than ever before, but we've also created new vulnerabilities. Digital storage requires continuous energy input to maintain. Hard drives fail, servers crash, file formats become obsolete. Without active curation and preservation efforts, digital information can disappear even faster than physical books. The internet has created an unprecedented experiment in information organization. Search engines like Google are essentially entropy-fighting machines, taking the chaos of billions of web pages and organizing them in ways that make specific information discoverable. Social media platforms try to organize the entropy of human communication, filtering and prioritizing the constant stream of posts, comments, and messages. But these systems also create their own forms of entropy. Filter bubbles and echo chambers can increase the disorder of public discourse by preventing the kind of information mixing that leads to understanding. Misinformation spreads like entropy through social networks, creating disorder in the collective knowledge of society. The challenge of content moderation is essentially an entropy management problem. How do you maintain the organization of truthful, useful information while filtering out the chaos of false or harmful content? As artificial intelligence becomes more sophisticated, it's taking on an increasingly important role in this entropy management. AI systems can process and organize information at scales that would overwhelm any human brain. They can detect patterns in chaos, find signals in noise, and help maintain the organization of human knowledge systems. But they also introduce their own forms of entropy algorithmic bias, unexpected behaviors, the risk of AI systems optimizing for metrics that don't align with human values. This is why the development of artificial intelligence is so crucial to humanity's long-term ability to fight entropy. If we can create AI systems that are aligned with human values and goals, they could become powerful allies in our ongoing battle against disorder. They could help us manage complex systems, solve global problems, and maintain the organization of human civilization at scales we could never handle alone. But if AI systems develop in ways that increase rather than decrease entropy, if they become sources of chaos rather than order, they could accelerate the breakdown of the organized systems we depend on. The alignment problem in AI isn't just about preventing robots from taking over the world. It's about ensuring that artificial intelligence contributes to the organization and flourishing of life, rather than its dissolution. Looking toward the future, entropy will continue to be the fundamental challenge facing any form of life or intelligence in the universe. As available energy sources become more scarce, as the universe continues to expand and cool, Maintaining organization will require increasingly sophisticated strategies. But the 4 billion years of evolution on Earth have shown us that life is remarkably creative at finding ways to harness entropy flows and build complex, beautiful structures. From the first self-replicating molecules to the vast neural networks of human civilization, from the earliest bacteria to the potential artificial minds of the future, the story of life in the universe is fundamentally a story about fighting entropy. Not by stopping it, that's impossible, but by riding its flows, channeling its power, and using it to build ever more sophisticated forms of organization. And that's perhaps the most inspiring message entropy has for us. Yes, the universe is running down. Yes, everything you love will eventually succumb to decay and disorder. But in the space between the organized past and the chaotic future, there's room for incredible beauty, meaning, and creativity. Every moment of consciousness, every act of love, every scientific discovery, every work of art is a temporary victory over entropy, a brief candle burning brightly against the cosmic dark. You are part of this story. Every choice you make about how to organize your time, your relationships, your efforts, is a choice about how to fight entropy in your small corner of the universe. The entropy you create by living is more than offset by the organization you can build in your own mind, in your relationships, in your contributions to the larger human project of maintaining and expanding knowledge, culture, and consciousness. The arrow of time points forward, toward increasing entropy and ultimate dissolution, but it's not pointing toward meaninglessness, it's pointing toward the incredible preciousness of the organized patterns we call life, consciousness, and love. Understanding entropy doesn't diminish the value of these things, it reveals just how extraordinary they really are. In the grand scheme of the cosmos, there's something almost rebellious about what happens on Earth every single day. While the universe marches steadily toward maximum entropy, toward heat death and ultimate disorder, our planet pulses with activity that seems to defy this cosmic trend. Forests grow, cities rise, children learn to read, scientists make discoveries. It's as if Earth has become a kind of entropy rebel, a small blue world that refuses to go quietly into that cosmic night. But here's the thing, Earth isn't actually violating the second law of thermodynamics. It's doing something far more clever. Our planet has become incredibly sophisticated at capturing and channeling entropy flows from external sources, primarily the sun. Every day, our star pumps enormous amounts of low-entropy energy toward Earth in the form of concentrated sunlight. Plants capture this energy through photosynthesis, converting it into chemical bonds while releasing waste heat. Animals eat plants, extracting energy while producing their own entropy, and humans have learned to harness these flows in increasingly complex ways. Think about the city you live in. From space, it looks like an impossibly organized structure. Roads laid out in grids, buildings arranged in patterns, lights twinkling in the darkness like a vast neural network. This organization exists because human society has become extraordinarily good at entropy management. We extract low-entropy resources like oil, minerals, and fresh water from the environment, process them through industrial systems, and create organized structures while dumping waste, heat, and disorder into our surroundings. But this process is accelerating in ways that would have been unimaginable just a century ago. The global economy now processes materials and energy at rates that dwarf anything in Earth's history. We're moving mountains, literally mining operations relocate billions of tons of rock every year. We're redirecting rivers, reshaping coastlines, and even changing the composition of the atmosphere itself. From an entropy perspective, human civilization has become a geological force, a planetary-scale entropy engine. And this brings us to one of the most pressing questions of our time. How long can this continue? Every economic system in history has eventually encountered entropy limits. Resources become depleted, waste products accumulate, complexity becomes too costly to maintain. The difference now is that we're approaching these limits on a global scale for the first time in human history. Consider climate change through the lens of entropy. When we burn fossil fuels, we're taking highly organized carbon compounds that took millions of years to form and converting them into carbon dioxide and heat a massive, rapid increase in atmospheric entropy. The climate system, which had reached a relatively stable state over thousands of years, is now absorbing this extra energy and reorganizing itself into new patterns. Unfortunately, these new patterns include more extreme weather, rising seas, and disrupted ecosystems. But here's what's fascinating. This crisis is also driving unprecedented innovation in entropy management. Renewable energy technologies are essentially entropy capture systems. Solar panels harvest the entropy flow from the sun before it dissipates as waste heat. Wind turbines capture atmospheric entropy generated by temperature differences across the planet. These technologies don't eliminate entropy production, but they work with natural entropy flows rather than creating artificial ones through combustion. Even more intriguingly, we're starting to see the emergence of truly circular economic systems, industrial processes designed to minimize waste by ensuring that the outputs of one process become inputs for another. In nature, there's no such thing as waste. Everything is food for something else. Leaves fall and become soil nutrients. Dead animals feed decomposers, which release nutrients for plants. It's a vast recycling system powered by the steady flow of solar entropy. Some forward-thinking companies and cities are trying to mimic these natural cycles. Industrial ecology parks where the waste heat from one factory powers another, where the chemical byproducts of one process become raw materials for a different industry. Urban farms that use food waste as compost and wastewater as irrigation. These aren't just environmental initiatives, they're entropy optimization strategies, attempts to squeeze more useful work out of every joule of energy that flows through human systems. But perhaps the most revolutionary development is happening in the realm of information technology. As we discussed earlier, there's a deep connection between information processing and thermodynamics. Every computation has an energy cost. Every stored bit requires physical resources to maintain. But we're rapidly approaching fundamental limits in how efficiently we can process information using traditional silicon-based computers. This is driving research into entirely new computing paradigms. Quantum computers that can perform certain calculations exponentially faster than classical machines, potentially requiring far less energy per computation. Biological computers that harness the incredible efficiency of cellular processes. Neuromorphic chips that mimic the brain's energy-efficient information processing. These technologies could dramatically reduce the entropy cost of the digital revolution that's transforming human society. And then there's artificial intelligence, which represents something truly unprecedented in the history of life on Earth. AI systems are essentially pattern recognition engines that can extract organization from chaos at superhuman speeds. They can find signals in noise, detect trends in data, and optimize complex systems in ways that would be impossible for human minds to achieve alone. But AI also raises profound questions about the future of entropy and organization in the universe. If artificial minds become sufficiently sophisticated, they might be able to solve problems that have puzzled humanity for centuries. Climate change, resource depletion, disease, poverty, these are all fundamentally entropy management problems. An artificial intelligence with access to vast computational resources and comprehensive data about global systems might be able to find solutions that dramatically improve humanity's ability to maintain organization in the face of entropy. On the other hand, AI systems themselves are major entropy producers. The data centers that train large language models consume as much electricity as small countries. The computational demands of AI are growing exponentially, potentially creating a kind of entropy arms race where we use more and more energy to build systems that can help us manage energy more efficiently. This paradox highlights one of the deepest challenges facing technological civilization: The more sophisticated our tools become, the more energy they require, and the more entropy they produce. It's like trying to fight a fire with gasoline-powered water pumps. We need the pumps to fight the fire, but the pumps themselves contribute to the problem they're trying to solve. But here's where human creativity and ingenuity come into play. Throughout history, whenever we've encountered entropy limits, we've found ways to transcend them through innovation. The agricultural revolution allowed human societies to capture more solar energy through farming. The Industrial Revolution taught us to harness fossil fuels. The information revolution is teaching us to process and organize information with unprecedented efficiency. Each of these transitions required us to discover new ways of working with entropy rather than against it, and there are hints that we might be on the verge of another such transition. Fusion power could provide virtually unlimited clean energy by harnessing the same nuclear processes that power the sun. Space-based solar collectors could capture entropy flows that never reach Earth's surface. Advanced materials could allow us to build structures that are far more efficient and durable than anything possible today. Even more speculatively, we might eventually develop technologies that can manipulate matter and energy at the quantum level with extraordinary precision. Molecular assemblers that can build complex structures atom by atom. Programmable matter that can reorganize itself on command. These technologies could allow us to create organized systems with entropy costs far lower than anything we can achieve today. But regardless of what specific technologies emerge, the fundamental challenge will remain the same: how to maintain and expand the organized complexity of human civilization while working within the constraints imposed by entropy. This isn't just a technical problem, it's also a social and political one. Managing entropy effectively requires coordination at scales from individual choices to global governance. Consider something as simple as traffic congestion. From an entropy perspective, traffic jams represent a breakdown in the organization of transportation systems. Too many vehicles trying to occupy the same space at the same time creates disorder that propagates through the entire network. Solving traffic problems requires not just better roads or more efficient engines, but coordinated systems that can optimize flows across entire metropolitan areas. The same principle applies to much larger challenges: climate change, biodiversity loss, resource depletion. These are all symptoms of entropy mismanagement at a planetary scale. Addressing them requires unprecedented levels of coordination between nations, industries, and individuals. We need to think of human civilization as a single, integrated entropy management system rather than a collection of competing entities. This is where the concept of collective intelligence becomes crucial. Just as individual neurons in your brain work together to create consciousness, individual humans working together can create forms of collective intelligence that are far more capable than any individual mind. The internet has given us the technological infrastructure for this kind of coordination. Social media, despite its problems, demonstrates that billions of people can share information and coordinate activities in real time. The question is whether we can harness this collective intelligence to solve entropy management problems before they overwhelm our capacity to respond. Can we create global systems that can monitor resource flows, predict system failures, and coordinate responses across cultures and political boundaries? Can we develop economic incentives that reward entropy efficiency rather than just short-term profits? Can we educate people about entropy and its implications in ways that motivate better individual choices? These questions become even more urgent when we consider that we might not be alone in facing these challenges. If life exists elsewhere in the universe, it's almost certainly dealing with the same fundamental entropy constraints that govern life on Earth. Any technological civilization, anywhere in the cosmos, will eventually encounter limits to growth, resource depletion, and entropy accumulation. This raises fascinating questions about what advanced civilizations might look like. Would they develop technologies so efficient that their entropy production becomes negligible? Would they spread across multiple worlds to distribute their entropy load? Would they eventually transcend biological limitations entirely, becoming pure information patterns that can exist with minimal energy requirements? Some scientists have speculated about Dyson spheres, hypothetical megastructures that could capture most or all of a star's energy output. Such structures would represent entropy management on an astronomical scale, allowing civilizations to harness stellar energy flows directly rather than relying on the tiny fraction that reaches planetary surfaces. Building such structures would require materials, science, engineering capabilities, and coordination that far exceed anything humans can currently achieve, but they're not necessarily impossible. Other possibilities include computational substrates that could support vast numbers of digital minds while consuming relatively little energy. If consciousness really is substrate independent, if minds can exist as patterns of information rather than biological processes, then the carrying capacity of the universe for intelligent beings could be vastly larger than the carrying capacity for biological life. These speculations might seem like science fiction, but they're grounded in serious scientific principles. The laws of thermodynamics don't disappear at large scales. They become even more important. Any civilization that wants to survive and thrive over cosmic timescales will need to become extraordinarily sophisticated at entropy management. And this brings us back to the arrow of time and its deepest implications for consciousness and meaning. We've talked about how entropy creates the direction of time, how it makes the past different from the future. But there's something even more profound happening here. Entropy doesn't just create time's direction, it creates the possibility for stories, for narratives, for meaning itself. Think about what makes a story compelling. It's not just a sequence of events, it's a sequence of events where each moment builds on the previous ones, where past actions have consequences for future outcomes, where characters grow and change and learn. This narrative structure is only possible because of entropy's arrow. In a universe without entropy, where all moments were equivalent, there could be no character development, no plot progression, no meaningful change. Your life story is fundamentally an entropy story. You began as a single fertilized cell, a tiny spark of organization in the vast chaos of the universe. Through an incredibly complex process of growth and development, that initial organization expanded into the sophisticated pattern of matter and energy that is your adult self. Every experience you've had, every relationship you've formed, every skill you've learned has added new layers of organization to your personal entropy management system. But your story doesn't exist in isolation. It's part of larger stories, your family's story, your community's story, humanity's story, life's story on Earth, the universe's story of increasing complexity and organization. Each of these stories is nested within the others, creating a vast hierarchy of narratives, all flowing in the same direction, all driven by entropy's inexorable arrow. And here's something that might surprise you. The fact that these stories have endings doesn't make them meaningless. It makes them precious. The temporary nature of organization in an entropy-driven universe isn't a bug, it's a feature. It's what gives weight to our choices, urgency to our actions, poignancy to our connections with others. If patterns could persist forever without effort, if organization were permanent and unchanging, then nothing would really matter. Every choice would be reversible. Every loss could be undone. Every moment would be equivalent to every other moment. It's the fact that entropy is always lurking, always threatening to dissolve the patterns we care about, that makes those patterns valuable. This is why entropy isn't the enemy of meaning. It's meaning's essential partner. The universe's tendency toward disorder creates the conditions where temporary pockets of order become precious, where the brief flowering of consciousness becomes miraculous, where love and beauty and knowledge shine all the brighter against the backdrop of cosmic chaos. And as we look toward the future, as we face the challenges of managing entropy on scales from personal to planetary to cosmic, we can take inspiration from the fact that we're not just passive victims of thermodynamic forces, We're active participants in the universe's ongoing experiment with organization and complexity. Every thoughtful choice you make, every act of creation, every moment of connection with another conscious being is a small victory in the eternal dance between order and chaos. The arrow of time points forward, toward increasing entropy and ultimate dissolution, but it also points toward endless possibilities for new forms of organization, new expressions of complexity, new ways of creating meaning and beauty in the brief time we have. Understanding entropy doesn't diminish the significance of human existence, it reveals just how extraordinary and precious that existence really is. You are a temporary but magnificent pattern in the vast tapestry of cosmic entropy, a walking, thinking, feeling example of the universe's capacity to create organization, consciousness, and purpose from the raw materials of space, time, matter, and energy. And that's not a small thing, that's everything. So what does all this mean for you, right here, right now? What does entropy tell us about how to live in a universe that's constantly moving from order to disorder? Well, understanding entropy changes everything about how you see your daily choices, your relationships, and your place in the cosmic story. Let's start with something simple that you probably experience every single day: procrastination. You know that feeling when you have something important to do, but you keep putting it off? That's entropy in action. The organized state where your task is completed requires energy input from you. The disorganized state, where it remains undone, is the natural default. Your brain, being an entropy processing system itself, will always tend toward the path of least resistance, unless you consciously apply energy to fight against that tendency. But here's the fascinating part once you understand this. Procrastination becomes less about moral failing and more about energy management. When you're procrastinating, you're not being lazy. You're experiencing the fundamental force that governs everything from gas molecules to galaxy formation. The solution isn't self-criticism, it's strategic energy allocation. This is why successful people often talk about habits and systems rather than motivation. Habits are essentially entropy-fighting mechanisms that reduce the energy cost of maintaining organization in your life. When brushing your teeth becomes automatic, when exercise becomes routine, when healthy eating becomes habitual, you've created systems that maintain order without requiring constant conscious effort. You've outsmarted entropy by making organization easier than disorganization, and this extends to your relationships in profound ways. Every meaningful connection you have with another person is a victory over entropy. Think about it, there are billions of people on this planet, but you've somehow found your way to specific individuals who matter to you. The probability of any particular relationship existing is astronomically small. Your friendship with your best friend, your love for your family, your connection with a romantic partner, these are incredibly unlikely patterns that emerge from the chaos of human possibility. But maintaining these relationships requires constant energy input, just like maintaining any organized system. You have to communicate, you have to be present, you have to work through conflicts and misunderstandings. The relationships that last aren't the ones that never encounter problems, they're the ones where people consistently invest energy in fighting relational entropy. When you understand this, it changes how you approach conflict. Arguments and misunderstandings aren't signs that a relationship is doomed, they're natural consequences of entropy acting on complex systems. Two conscious beings trying to maintain connection will inevitably encounter moments where their communication breaks down, where their expectations misalign, where disorder creeps into their shared understanding. The question isn't whether this will happen, it's how you'll respond when it does. This is why forgiveness is so powerful from an entropy perspective. Holding grudges, maintaining resentment, refusing to repair damaged connections, these behaviors increase the entropy of your social systems. They turn organized relationships into disordered ones. Forgiveness isn't just morally admirable, it's thermodynamically efficient. It allows you to restore organization to systems that entropy has disrupted. Now let's talk about learning and personal growth. because this is where entropy gets really interesting. Every skill you develop, every piece of knowledge you acquire, every habit you build is a form of organization in your neural networks. Your brain is constantly forming new connections, strengthening useful pathways, and pruning away unused ones. Learning is literally the process of organizing information in your mind. But here's what most people don't realize: learning is uncomfortable precisely because it involves entropy. When you encounter new information, especially information that challenges your existing beliefs, you experience cognitive dissonance. Your mental models become temporarily disorganized as your brain tries to integrate conflicting data. This feels unpleasant because your consciousness is experiencing entropy increase in real time. The students who succeed aren't the ones who find learning easy, they're the ones who develop tolerance for this temporary discomfort. They understand that the confusion, the uncertainty, the feeling of not quite grasping something yet, these are natural parts of the learning process. They're entropy phenomena that you have to work through, not around. And this connects to something profound about creativity and innovation. Some of the most important breakthroughs in human history have come from people who were willing to let their thinking become temporarily disorganized. When you allow random inputs into your mental processes, when you make unexpected connections between unrelated ideas, when you question assumptions that everyone else takes for granted, you're introducing controlled entropy into your thought patterns. This is why so many creative insights happen during activities like walking, showering, or doing repetitive tasks. These activities occupy your analytical mind just enough to allow more chaotic, associative processes to take over. You're temporarily increasing the entropy of your thinking, which creates space for novel patterns to emerge. But creativity isn't just about individual insights. It's about contributing to humanity's ongoing battle against intellectual entropy. Every work of art, every scientific discovery, every technological innovation adds organization to our collective knowledge base. When you create something new, something beautiful, something useful, you're participating in the universe's most ambitious project, the creation of meaning and complexity from the raw materials of space, time, and energy. This brings us to something that might change how you think about success and failure. In a universe governed by entropy, failure isn't the opposite of success, it's part of the process. Every failed experiment, every relationship that doesn't work out, every project that doesn't succeed is the universe's way of exploring the space of possibilities. Entropy ensures that not all patterns will persist, but it also ensures that new patterns can emerge. The people who achieve remarkable things aren't the ones who never fail, they're the ones who fail efficiently. They extract information from their failures, learn from their mistakes, and use that knowledge to build better systems. They understand that in an entropy-driven universe, the only true failure is not trying, because not trying means not contributing any information to the universe's ongoing experiment with organization and complexity. And this perspective can be incredibly liberating when you're facing difficult times in your life. When you're going through a breakup, when you've lost a job, when you're dealing with illness or grief, or any of the countless challenges that entropy throws at us, these experiences aren't punishments or signs that you're doing something wrong. They're natural consequences of living in a universe where all patterns are temporary, where all organization eventually gives way to disorder. But temporary doesn't mean meaningless. The relationships that end still contributed to who you are. The jobs you've lost still taught you valuable skills. The challenges you've overcome still built resilience and wisdom. In the grand entropy accounting of your life, these experiences didn't decrease your overall organization. They added new forms of complexity, new layers of understanding, new capabilities for creating meaning in the face of chaos. This is why gratitude is such a powerful practice from an entropy perspective. When you take time to appreciate the organized patterns in your life, your health, your relationships, your opportunities, your experiences, you're acknowledging the incredible improbability of your existence. You're recognizing that in a universe trending toward disorder, the fact that you can think these thoughts, feel these emotions, experience these moments is nothing short of miraculous. And gratitude isn't just about appreciating what you have, it's about recognizing your role in the cosmic story of increasing complexity. You're not just a passive observer of the universe's evolution, you're an active participant. Every choice you make about how to organize your time, your energy, your attention, contributes to the overall direction of entropy in your local region of space-time. When you choose to learn something new, you're decreasing the entropy of your knowledge state. When you create something beautiful, you're adding organization to the world. When you help someone else, you're contributing to the maintenance of social systems. When you take care of your health, you're fighting biological entropy. These aren't just personal choices, they're cosmic choices, small but meaningful contributions to the universe's ongoing experiment with order and complexity. This brings us to perhaps the most important implication of entropy for how you live your life, the recognition that your time is finite and precious, precisely because it's bounded by thermodynamic limits. You have roughly 80 years of consciousness, give or take. During that time, you'll process an enormous amount of information, form countless memories, build numerous relationships, and contribute in ways both large and small to the ongoing human story. But you can't do everything. You can't experience every possibility, learn every subject, visit every place, meet every person. Entropy imposes constraints, and those constraints force you to make choices about how to allocate your most precious resource, your conscious attention during your brief time as an organized pattern in the cosmic flux. This is why it's so important to be intentional about these choices, not because there's a right way to live, but because every moment of consciousness is irreplaceable. Every day you spend in patterns that don't serve you, every hour you waste on activities that don't contribute to your growth or the growth of others, every minute you lose to mindless consumption or pointless worry, these represent entropy victories that you can't get back. But this isn't meant to create pressure or anxiety. It's meant to create appreciation. When you truly understand that your consciousness is a temporary victory over entropy, that your capacity for love and learning and creation will eventually give way to the same forces that govern cooling coffee and aging stars, it doesn't make life meaningless. It makes every moment infinitely precious. The entropy perspective reveals that you're participating in something much larger than yourself. Your individual story is nested within humanity's story, which is nested within life's story on Earth, which is nested within the universe's story of evolving complexity. You're a character in the greatest narrative ever told, the story of how matter and energy learn to think, to feel, to create meaning in the face of inevitable dissolution. And here's the beautiful paradox at the heart of it all. Entropy isn't just the force that will eventually end your story. It's also the force that makes your story possible in the first place. Without entropy's arrow, there would be no time, no change, no growth, no possibility for the kind of consciousness that can contemplate its own existence. The same thermodynamic principles that ensure your mortality are the ones that make your life meaningful. So, as you go forward from this moment, as you make choices about how to spend your finite time and energy, remember that you're not just managing your personal entropy, you're participating in the universe's most ambitious project. You're part of a cosmic experiment in creating order, beauty, and meaning from the fundamental forces of physics. And that's not a small thing to be, that's the most important thing to be. The arrow of time points forward, carrying you and everything you love toward an uncertain future. But it's not pointing toward emptiness, it's pointing toward infinite possibility. Every day brings new chances to create, to connect, to learn, to contribute to the magnificent, temporary, utterly improbable experiment that is conscious life in an entropy-driven universe. And with that understanding, with that sense of your place in the grand cosmic story, you can face tomorrow not with fear of entropy's inevitable victory, but with excitement about what new forms of organization, What new expressions of complexity, what new moments of beauty and meaning you might help bring into existence during your brief but brilliant time as a walking, thinking, feeling victory over chaos. The universe gave you consciousness, and consciousness gave you the ability to understand entropy. Now, entropy has given you something even more precious. The knowledge that in a cosmos trending toward maximum disorder, your capacity to create order, to build meaning, to love and be loved represents something genuinely miraculous. You are the universe becoming aware of itself, if only for a moment. Make that moment count.